A very good afternoon to all the participants for this session being present over here. I welcome I welcome Dr. Svitlana Ijenko for this program. I now have immense pleasure in introducing our speaker for this session. Dr. Svitlana is material scientist with a specialization in material science, that is phase equilibria, phase diagram, crystallography, morphology, and thermodynamics. She has a PhD in physical chemistry from Ukrainian Academy of Science in Kiev. Dr. Svitlana has also had postdoc positions in Max Planck Institute for Material Research in Stuttgart, University of Vienna, and University of Montpellier. She has also engaged for over 20 years in German company Material Science and International Services GmbH MSI, which is a research and publishing institution in the field of material science. Dr. Svitlana is also editor and co-editor for more than 25 volumes of handbooks on critical evaluation of material constitution data, and she is also an ex officio member of editorial board of MSI Eureka Knowledge Base. Since 2018, Dr. Svitlana is CEO of MSI. This is just a brief note on her experience. So I would also now ask Dr. MMR Rajat Hegde sir to introduce our guest. Sir?
Are you able to hear me?
Yes, sir. Yes, sir. Your voice is audible.
Yeah. Good morning, Svitlana. Svitlana Iljenko, Dr. Svitlana is a Chief Executive Officer at the Material Science International Forum. This Material Science International Forum is associated with Max Planck Institute, Stuttgart, Germany. And she has conducted a number of workshops on phase equilibria, and she has done a lot of work on binary phase equilibrium diagrams, ternary and multi-component equilibrium diagrams. I have been associated with her since almost 5 to 6 years, and I was supposed to attend 2 such international workshops on phase equilibria at Ringberg Castle in Germany. But unfortunately, due to the pandemic situation that is happening everywhere throughout the world, they had to cancel the offline workshop, and they had to switch it on to online mode. Anyway, probably in the near future, when the pandemic situation comes to a situation where each one of us can attend personally all the offline sessions, hopefully I would like to go there and participate in one such international forum. Thank you, Svitlana, and over to you.
Dr. Svitlana, it's not audible. Would you please unmute? No, it is still isn't audible. No, we're still not able to hear you, ma'am.
How it is now?
Yeah,
Now it's audible, ma'am.
yeah, we are able to hear
Oh,
you. Yeah,
okay.
fine.
So I
Fine.
just had to plug out my headset somehow. It stopped working. Thank you very much for the nice introduction. First of all, I would like to thank the National Education Society and the Department of Mechanical Engineering, in particular, Professor Rajat Hedge, for inviting me to give a talk about our activities at your meeting. I'm very much impressed by the number of participants which you have in this conference. And indeed, I hope very much that in the future we can establish a more close cooperation with your department, and you can attend also our meetings once pandemic is over. Now, let me start with the topic. The topic of my talk will be about the importance of critical evaluation of data in multi-component phase equilibria, so in phase diagrams in materials constitution. Let me just prepare everything so that for the transaction and okay. Can you see the next slide now?
Yeah, we can see. Yeah.
Okay. Then I continue. Let me start with some terms and abbreviations which I will use in my presentation so that you can follow me further. MSI Eureka is the name of a materials database with the main focus on materials constitution. That means phase diagrams, phase equilibria, and all related topics like crystallography, thermodynamics, morphology, and other properties. The database is created with the efforts of a large international team, Materials Science International team, who are experts in the field of materials constitution. And MSI, this is the name of the company who owns the database and coordinates activities of the MSI of this team. MSI is involved not only in publishing, but also in research and consultancy services and educational events. And the company is located in Stuttgart in Germany. Let me, somehow my transition doesn't go smoothly. So the company is actually a spin-off from the Max Planck Institute for Metals Research in Stuttgart. In 1984, Dr. Günther Effenberg, whom you may know, started to gather a group of well-known experts in the field of phase equilibria and thermodynamics. That was actually the beginning of the MSI team. In those days, the aim of the project was to publish the detailed compendium of critically evaluated ternary alloy phase diagrams. This project started, and since 1990, it continued already as a company effort. MSI was formed, and yeah, somehow I get a problem with transition. Okay, let me follow here. So at the early beginning, these were the people who started jointly developing standards for critical evaluation of ternary systems. Many famous names you can see here, like Alan Prince, whose book for phase equilibria is very known in all countries. Professor Ricardo Ferro, Peter Rogel, Rainer Schmidt-Fetzer, Leo Lucas, who is well known for the calculations. And for over more than 35, it's already actually 36 years, more than 280 scientists have contributed to this project. Their affiliations you can see here on the right side. They are spread over 5 continents. The activities of MSI and MSIT are related not only to publishing. We are in the middle of research, running and coordinating various research projects, national, bilateral, European, etc. Once a year, we meet with our team already since 35 years. We meet every year at the nice castle, which Rajat mentioned already, Rheinberg in Germany, in Bavaria. where we conduct the work on critical evaluation of multi-component systems. And 5 years ago, we also started a series of educational events. So we this is called MSIT Winter School on Materials Chemistry. And it turned to be very popular, and not only among young scientists, but also many professors and R&D professionals from industry take part in order to refresh their knowledge. The output of the activities of this team is present in many libraries in the world, in the academic libraries. We have published over 60 volumes of printed books. For example, Ternary Alloys, this is the book series where we started on critical evaluation of different ternary systems. We went initially by categories covering ternary system of each particular element. So one of them was 3 volumes of the magnesium ternary systems. This project started jointly with Wiley VCH and later continued by MSI on its own. In the recent years, we also published 2 volumes. However, we have changed the strategy slightly. Now we are not following the alphabetic order by elements, but we select interesting topics. For example, one of the last volumes was on nuclear materials, or the next one was on solders materials, and the next one is coming on aluminium iron containing systems. Another book series, Landau-Bernstein, which you may also very well know from the libraries. It's also handbooks, and we prepared 17 volumes in this book series. Also jointly with Russian Scientific Service, we published red books where we extracted from the literature all constitutional data from each publication and presented them in the books as well as electronically. With American Society for Metals, we also have published 3 books. It's a metal boron carbide and pressure-dependent binary phase diagrams. But already in the earlier days of the MSIT, the compilation of an electronic database started, which included and includes not only the content of the books, but also other data categories. Let me give you an overview about materials types included in MSI Eureka. The following groups of inorganic material systems are presented. These are alloys, non-metals, and some composite materials like metalloceramics. Not included ionic liquids, and of course no CH bondings are included. And for the following materials types, we have the following information. This is materials constitution, which is, yeah, I think I don't need to explain in this audience. Let us go to the next slide. And here I would like to cite the Alan Prince. You may know his book about phase diagrams. A metallurgist has been defined as a person who thinks in terms of phase diagrams. And for us, this is a very important sentence, which actually tells us that materials constitution of phase diagrams, this is a very important and very basic and fundamental topic in material science, which actually gives the most basic information about materials behavior. And this one should not forget when doing, in particular, when starting any research. Let us look in the definition what is phase equilibrium and phase diagram. Phase equilibrium, we know phases are in equilibrium with each other when the Gibbs energy of the system reaches a minimum. For the phase diagram, there are different definitions in different resources. My colleagues here has found a couple of them. For example, Mats Hillert, also well-known name in the calculation of phase diagram, He formulated it as a state diagram with some additional information, what phases are present under various conditions. Very simple formulations and exact. Alan Prince formulated it nothing more than a presentation of data on the position of phase boundaries as a function of temperature. And Wikipedia gives a more complicated formulation, a type of chart used to show conditions at which thermodynamically distinct phases occur and coexist at equilibrium. Everything is correct. And what information can we get from a phase diagram? So of course, there are different types of phase diagrams. We will focus now on phase diagrams, which are usually representation of a system A, B, and maybe a more component C, and so on, which show the equilibrium phases and the phase equilibria among them, independence on the two state variables, temperature and composition, at a constant pressure of 1 bar. What information can we get from the phase diagrams, just when we look on the phase diagram? So first, which phases exist? Homogeneity ranges of the phases, their extension, phase equilibria at a given temperature or composition. Also, melting temperature at a particular composition from the solidus. Melting behavior of phases, whether they melt congruently or incongruently, by which reaction. Compositions of coexisting phases. Phase fractions we can get from the phase diagram, type and temperature of invariant reactions, cooling and heating path. Except for that, there is more information which one can get from the phase diagram, maybe not directly, but get some hints. Many properties, for example, scale with the melting temperature, or one can get hints on the synthesis of specific phases or specific particular alloys. And also hints on alloy development strategies, which composition should be selected, at which cooling rates it's better to prepare, what microstructure will we expect in this case. And of course, on processing of the alloys, selecting, for example, heat treatment conditions. This all can be read from the phase diagram. And now I'm going back to our database, MSI Eureka, and just few words how it is created. We presented it as a staircase, and the database is created by adding value to information which can be found in the scientific literature. On the first level of this staircase, we have literature monitoring. We monitor permanently over 250 journals and identify articles which are relevant for materials constitution of inorganic materials. In fact, this is a bibliographic database, which is the starting basis for all other data categories. So to this information, we add abstracts, we add information about crystal structure of solid phases, and we redraw phase diagrams from the literature. And the highest value in the database is with critical evaluation of all available data. Now, let us focus on the critical evaluation of data. Why do we evaluate? Those of you who is working with phase diagrams, at least from time to time, certainly could notice how often data are inconsistent or conflicting in our field of science. They can be conflicting even within one publication if, for example, isothermal and vertical sections do not match, or liquidus and solidus. And the conflicts between different publications originate from the following factors. These are different types of measurements. They are different by nature. Some of them are static, some are dynamic, measured or observed. And respectively, they bring different accuracy and precision. Also different quality of starting materials and poor or unsuitable practice. Let me close this. Where was and respectively pure or maybe unsuitable experimental practice turns often as the reason for non-precise data. And also an important and often happening factor is incorrect interpretation of raw data caused by brings a lot of errors. All these aspects play a large role because phase diagrams cannot be measured, but they are concluded from different types of experiments and from their combinations. It is indeed a complicated scientific field requiring highly specialized expertise, which is not always involved in the interpretation of the raw data. And as a result, many contradictions in literature. And the user and the scientists or the reader, they need a single diagram or a set of complementary diagrams in case of a multi-component system, which they can trust, and preferably they should come from one source. Now I go in more details. Actually, this slide, I think I already integrated in the previous slide. Let me just continue. So user, as I told, needs a single diagram or a set of complementary, and preferably these diagrams should come from a trustworthy source. And this is what we try to create with the efforts of our scientific team. If I had to formulate what means critical evaluation very briefly in one sentence, I would put it down to these 4 points. It's find conflicts in literature, point out them, settle conflicts where it's possible, it's not possible always, and give arguments for rejecting or accepting or amending data. So this was a brief summary of what critical evaluation means. In fact, critical evaluation is the task to produce in a concise and easily readable form a set of self-consistent phase diagrams and thermodynamic properties that represent the current and the best state of the knowledge of a particular system. This requires a careful consideration of all experimental and theoretical work carried out on the system under consideration. Thorough literature search is, of course, a prerequisite, and we also consider the review articles, not only the original research, but they can be useful, but we always try to go back to the original data and evaluate the original data, not the other reviews. Here are our criteria to check the reliability of data in the process of critical evaluation. We check purity of initial materials. What actually we check, yeah? So we check purity of initial materials. We check sample preparation, heat treatment conditions, and experimental methods. All these verifications should be made reflecting their suitability for this particular material under consideration. What is suitable for one material will be not suitable for the other material. And we check compatibility with results from thermodynamics. By the way, thermodynamic modeling can be used by our authors as a tool assisting the intellectual critical evaluation, but it is not a requirement, and because it is all about intellectual critical evaluation, what we do. And calculations can be used only to assist as a tool. If we look on the experimental steps and methods which scientists ideally apply in their research when they want to construct phase diagram or find out just phase equilibrium, then it looks like that. So we start with choice of suitable alloy compositions. We continue with synthesis of alloys from the elements, or alternatively, there are other methods like diffusion couples. We make chemical analysis to find the impurities and to determine exactly the bulk composition of the ready material. The next step is heat treatment to get equilibrium condition. Next is an important aspect is metallography for microstructure inspection, which the method which is sometimes underestimated, but it is a very important method in understanding material behavior, and analysis of the crystal structure of the phases to identify them, and of course thermal analysis to establish all transformation temperatures. And if needed, there are more advanced methods like term neutral diffraction, backscattered diffraction, and so on. Important on this slide is this sentence. Ideally, if somebody investigates phase equilibria, he should apply a combination of complementing method. And this is also an important factor which helps during critical evaluation. If published data are supported by different methods, they most likely will be considered by us, by our authors, as more reliable compared to the diagram which is derived from only one type of experiments. So now, what else we check in the literature when we make critical evaluation? We check the correctness, of course, with respect to the rules of heterogeneous equilibria. Then we check the compatibility between binary and ternary data. And when checking compatibility of binary and ternary data, it is important indeed first to evaluate the data on the binary system and then go back to the ternary. If we find conflicts between binary and ternary system, then this is indeed a challenging question to decide who is guilty, where is the fault with the binary or with the ternary data. Also, we check compatibility of intersecting sections like isothermal and vertical sections. We check compatibility of consecutive sections or surfaces. For example, isothermal sections at different temperatures, whether they indeed match with each other in the way that it is feasible. The change of if within 1 degree Celsius 10 phase transformation would happen, this most likely is unlikely, let me say. Or we check compatibility of the liquidus and solidus surfaces. We check interpretation of measured experimental values against the conclusions of the authors of the original publications. And indeed, if the raw data are given in the original article, our experts may reinterpret this data and come up with a different phase diagram. And this indeed happens often, or at least partially. Therefore, the depth of experimental details in the publication is also an important parameter that helps to verify the reliability of the published data. And therefore, I'm always encouraging scientists to, when you publish your data, please give as much as possible data, raw data, measured data, just measurements in the table form, in as DTA curves and so on. This is really helpful for other scientists when looking at your publications. So critical evaluation, first of all, is an intellectual process. So we examine all literature which we have on a particular system. We split it in basically 3-4 topics like phase equilibria, crystal structures, thermodynamics, and physical properties. The 3 first are, of course, the most important. And we check for consistencies and conflicts. Why do some data agree with each other and the other data sets not? And we try to find which are the best data sets applying the methods which I just mentioned before. And in the ternary data, of course, if the problem with the binary system, this I also mentioned already, this is, again, sometimes we have to go to the binary systems in order to decide how to continue with, if the contradictions between on the boundary borders of the ternary system appear between binaries and ternaries, or between different binaries which were accepted in the ternary and brought to these inconsistencies. So we check also for gaps in the data. And some publications, of course, report only particular composition or temperature range. And it happens that in the literature we don't find data for particular regions in the phase diagram. And then our task is to check whether it's possible to extrapolate in order to fill the gap in the knowledge. At this point is thermodynamic modeling is helpful, but not necessarily. It's also possible intellectually to give a suggestion to how to continue, whether it's possible to extrapolate in the unknown regions. And we try to be objective and don't bring much speculation in this. So then this slide is actually kind of last wish from the editors to our authors when we start, for example, our group walk in the castle of Rinberg. Then just the most important things which the authors should remember when walking are the following: be critical, be objective, and explain any choices that are made between data sets. Why rejected, why accepted, and we try to do it in details and always give arguments. All conflicting diagrams should be discussed in the text. We cannot reject something by just not mentioning it or not telling anything, not including in the list. No, this is exactly, we want to give an honest and a real situation to our readers and scientists who use our publication, explaining what we experts think is more reliable and what is less reliable. At the end, we select one set of diagrams, even if the others may be equally good or bad, and we justify the decisions in the text. If necessary, the author reinterprets published measured data versus published conclusions, and it may indeed come to a new phase diagram, or new parts of the diagram. And the output of the evaluation process is presented in the form of a publication. We call it system report or evaluation report. It considers all publications. It describes the system as a whole, not just a collection of different sections and projections. And it describes the steps and decisions taken in the critical evaluation process. At the end, we present best set of self-consistent information about the system the diagrams, tables, and text should be made consistent. And believe me, when we do it, we look in each publication, and we often find that even within one article, there are often data which are not consistent between diagrams and tables and text. There may be different types of reactions, different compositions given, and this is what we try to find out and sort out the problems. At the end, we generate consistent diagrams from many scattered data. And at the very end, all articles are peer-reviewed. Here, our procedure is also different from the other publishers. Our reviewers check not only the result of the work of our authors, but they check their conclusions against the original literature. That means they look in the same literature which our authors analyzed. And very often long discussions go between the authors, the reviewers, and the editorial staff at MSI, who are also PhD in materials science. This way allows us to ensure the high scientific level of our publications. Now I would like to show you some examples how critical evaluation works, or what are actually the results of critical evaluation, what that actually means. So we have here an example, hafnium, platinum, palladium system. In the year 1990, at 1000 degrees, the black, so the gray phase diagram was published, which actually supposed this continuous solid solution between these two stoichiometric phases, hafnium platinum and hafnium palladium. And later, the hafnium platinum binary system has been revised, and it was found that, let me find, yeah, the hafnium platinum phase actually has two different modifications, high temperature and low temperature. And obviously, the crystal structure of the low temperature phase is different from the crystal structure of the hafnium palladium phase, while high temperature phases have the same structure. But here we are at 1000 degrees in the binary system, and here indeed we have only the low temperature phase. And this is the task already of our authors, to see that, yes, this is not possible, so they cannot form a continuous series of solid solutions in the tannery if they have not the same structure. So the red lines, these are already redrawn by our authors by breaking this continuous solid solution. And if you make out of one phase now two, then of course there must appear other 2 and 3 phase equilibria, and they are shown here in dashed lines because they are not reliably established, but this is just the assumption of our authors. Since the continuous solid solution is not possible, there must be a 2-phase field, and this of course will cause existence of some other 3-phase fields here. And this is here is just part of text. I know this is not readable, but I described it already to you. What they also, our authors highlighted, that the authors of this original publication, this gray phase diagram, did not present primary experimental data to support their conclusions about the existence of the continuous solution here. And that means that indeed there were no data, just a ready result. So they have the same structure. We believe they have a continuous series of solid solution. If they had experimental data, that would make the job of our authors easier. So let us look to the next example. Here we have niobium aluminium. Now this is a ternary system, niobium aluminium iron, and here the red lines, this is a calculated diagram. Yeah. No, the red line is a critically evaluated diagram and the black one is calculated. The point here was that our authors had these two different work. One is experimental, one is calculated. And here the preference was, the conflict was about this temperature of this invariant reaction. And for the rest, the agreement between calculated and experimental phase diagram is very good, but only in this area the disagreement is very large. It's almost 100 degrees or 50 degrees, 70 degrees. And here the preference was given to the experimental data, which obviously were more reliable, considered as more reliable. And therefore, in red, you see the phase diagram, which is here in this area was amended by our authors. All this is well described in the text and the user can follow why these changes have been made. Another example, just to see, sometimes we re-evaluate a number of the most important systems, particular for different sorts of applications, or which on potential applications also. They gain a lot of attention, and there are many new publications appearing every year, and we repeat our critical evaluation in this case, because in this case, for example, the publication from 1992 is compared here with the 2013, and this is only one figure which just show the locations of the all ternary phases which were reported in this ternary system are shown just as a compositions here, and you see the difference and the number of publications which appear within this 20 years or something like that. So we do update our evaluations, but of course not for all systems, but only for some of them. The next example is liquidous surface in the aluminium iron silicon system, and this is again, both are evaluation reports, our publications. One is from 92, 93, and another one is from 2013. And you see that we also changed our mind depending on which data are published, and the liquidus is, in principle, it's not dramatically changed, but it is different based on the new data which were evaluated to be more reliable. Another example. Here, an interesting point was about the existence of previously reported tau 1 and tau 9 phases. These are ternary phases, which are traditionally called tau. These are this composition and this composition. Later, in the later work, it was found that in fact there are no two, this is only one phase. And respectively, the equilibria also have been changed. Now they are joined in one, respectively some 2 and 3 phase fields have disappeared from the diagram. And the last example is very peculiar. This is one of the most strange cases where which we have seen in published articles. I can give you a minute to search for funny mistakes in these diagrams and in the figure caption. You can just switch your microphone on and tell me whether you can see strange features on this diagram. Look at the 3 phase fields, the tire triangles, so-called, how they look funny here. The tire triangles, or the tire lines, let us start with tire lines. They are straight lines. And the tire triangle, this is really real triangle with straight lines. In this diagram, this is very unusual. Such mistakes really don't come often in the literature, but somehow it escaped also the review processes of one journal. And here, these tire triangles, they have curved lines, which is absolutely impossible. Tire lines show just graphical representation of two compositions of two faces, so they cannot be curved. And yeah, this is a very special case. Also, the black fields, this is a clear single phase fields, and in the figure caption it states that these are two phase domains, which cannot be because they are bordered by two phase domains here. So this is a funny case which sometimes also happens in the world literature when we evaluate data. So the next case, I'm ready now with the examples of critical evaluations. We will look later on some magnesium systems. Now I'm back to our database to introduce you other data categories. If you remember to my staircase, which I have shown before, at the bottom there was links to literature, which is in fact a bibliographic database which correlates materials with relevant publications. Important, it delivers only relevant results due to this direct correlation between publications and system. And this correlation is established by humans. We are not searching in other resources. We really look in each article and identify which systems are reported, which are the keywords, what topics are covered, and whether it's relevant for our database. This way allows us to provide a delivery of only relevant results. By now we have over 490,000 citations, which are related to more than 75,000 systems, and coverage of relevant literature often is better than the large bibliographic databases, which you may know, like Inspect or Web of Knowledge, exactly because we are focusing only on our field of knowledge. Now I would like to present you another data category in the database. It is called diagrams as published. Contrary to the previous category of critical evaluations, here we find diagrams that are not evaluated by MSI team. They are redrawn from the original publications, but we always add information about crystal structure of solid phases, because otherwise diagrams generally are not readable if stoichiometry and crystal structure are not presented. Here, for example, you see that for the same system there are two liquidous surfaces which are quite different. If you look in this area or here also, they are different here. They originate from different publications. On the contrary, in a critical evaluation, which I presented just before, there will be always only one liquidous surface presented, evaluated and chosen by, evaluated or composed by our experts as the best choice. In this case, we present everything as it is, not evaluated. And another data category, research results, which present extended extracts from the literature, only on constitutional data. Initially, this was the project Red Books with the short abstracts which were published. And from this year, we started publishing their brief original publications. And another data category, pressure-dependent binary phase diagrams, written by one author. This was also one of the books which we published. And so there are different 188 binary systems which have different sorts of pressure-dependent diagrams. So this was briefly about other data categories which are less important. Now back to MSI Eureka and for whom actually this database is useful. First of all, these are, of course, scientists and engineers in both in academic and in corporate world, for R&D professionals, for educators, and for students. It's often used in teaching classes. For information managers like librarians, that's also most of our, or many of our customers. These are libraries which take licenses, subscriptions for their universities. And for science managers, program officers, in particular at the stage of choosing or planning projects. And for these three groups, these three groups, they are applied in the following fields and industries: physics, chemistry, engineering, material science, and so on, and also multiple industries. It's really difficult to name industry where material science data wouldn't be required. Therefore, the list is only tentative, of course. Let us look at the situations where MSI Eureka is typically used. First is at the stage of planning and executing projects, one can quickly find what is known and even what is unknown. This is thanks to a convenient search interface via the periodic table, which I will show you later. Second area is very important: computer-aided material science and simulations. Evaluated data is actually an ideal source for computer modeling as an input of reliable evaluated data. Every calculation starts with input of data. It is well known that the output of a calculation directly depends on the quality of the input. When inputting data, one should assign weight to different data. Means the user first should evaluate and decide what is more reliable and what is less reliable. And in this step, one can save a lot of time when having data evaluated by the experts in this field. A third area, just looking at a phase diagram, one can get direct answers in daily laboratory work. Let me show just some examples. In this case, for example, for the electronic devices with silver copper phosphorus alloy, does this alloy offer melting temperatures that our devices can stand, means over lower than 800 degrees? The answer is coming from the liquidous surface of this ternary system. One looks at the composition of this alloy is here. It is located between two isothermal lines on the liquidous surface, 800 and 700. So one can estimate it as 770. That means that this alloy, which somebody would like to use, is possible to use in this device. If the next question then may come in this case, how critical will be the temperature control during this joining process? And how large, actually the question is how large is the melting range that this alloy has. This one can get by looking at solidus and liquidus temperatures, and the melting range, so the end of melting is 770, and it starts melting at this eutectic temperature, 646 degrees. So that means that the melting range is between these two temperatures, and the temperature control for this device will be not critical. That's quite a convenient, good candidate. Another example, in photolithographic processing, aluminum copper silicon alloy corrodes, and to reduce the corrosion, it corrodes because aluminum is precipitating, and to avoid the corrosion, they would like to make it so that the silicon precipitates primarily. And the answer is also on the phase diagram. So one should check actually how much aluminium can be substituted by copper before the primary solidification switches from aluminium to silicon. So the answer is also here. This is the initial composition which they had, and so they want to add copper to this. So we move along the copper concentrate, and as soon as we on the border between the yellow and the green field, so the primary crystallization phase is already silicon. Then we determine this composition and give the answer, okay, once you reach this composition, you can add a bit more of copper, but already starting with 9% of copper, you will have silicon crystallizing primarily from the melt. So just to summarize how Messiah Eureka helps to researchers, it helps to find information on particular material fast and comprehensive and only relevant information. It helps to understand the material system as a whole. And it helps to develop and design materials and get fundamental information in time and minimize number of experiments at the end. And it's also very useful in the planning and performing research projects. In the industry, the approach materials development or attempts to improve the existing material often start by trial and error method, trying blindly to change the composition or temperature or other conditions. Let's say I add silicon to my material, maybe an unwanted precipitate phase would disappear. And this approach brings often many trials without any result. Very often looking first at phase diagrams and the evaluated phase diagrams helps to minimize expensive experiments in R&D. One may see already on the phase diagram what makes sense to try and what not. And this is only a minimum. One can get much more answers on a phase diagram. We often tend to forget that the field of materials constitution, so actually knowledge on phase equilibria, is the most fundamental information about material behavior. And it should be obligatory known to R&D professionals at the very early stage of materials development, preferably. So now I will switch to the second part of my presentation about how to access data, and we look also at some live examples. So there are two alternative access options. One is in the browser interface, simply at msiaeureka.com, and another one is our legacy client software, MSI Eureka Viewer, which needs installation of the client software, but it has nice features which are very helpful, and this I will demonstrate you in the next slides. Yes, now I switch. I don't need this slide. I have to probably reshare somehow my screen because now I'm in the PowerPoint and I need to demonstrate you other windows. Let me just try to switch. I will first stop presenting and then I share my screen immediately again. Okay, here we are. Can you see my... Okay, now I hardly can see what you can see. Can anybody tell me whether you see the periodic table now on your screen?
Yes, we can see. Yes, we can.
Okay, okay, thank you. then I continue. So this is the browser interface of the database, and I will start. I selected a magnesium system, gadolinium, magnesium, neodymium, which is actually, to my knowledge, is also related to biomaterials, in the development of the biomaterials. So let me just click in the periodic table. It's because I was I do it again. Okay.
Dr. Svidlana, would you please unmute yourself? We are not able to hear you. Dear participants, Dr. Svidlana is experiencing a short problem on her network connectivity. So please stay logged in. Okay. I'm still, we are not able to hear your voice.
Okay. Can you hear me now? Can
Yes,
you hear
ma'am,
me
it's
now?
audible. It's clear. It's
Okay,
clear, ma'am.
good. Then can you see my screen now?
Yes, ma'am. Yes, ma'am.
Okay, good. I'm sorry for this interruption. Now okay. So I go back one step. I'm selecting now 3 elements: magnesium, neodymium, and gadolinium. And you see when I'm clicking in the periodic table on the elements, some of the elements become grayed out, yeah, and they are not clickable. I cannot click on them anymore. This is what I mentioned before. You can get information here on the information which is known and which is unknown. The point is, the meaning of this faded out elements is that when I selected 3 elements and want to add another one to them, I can add only that which is known, which was investigated by somebody, and therefore it entered our database. That means in the world scientific literature, there are publications on these systems, but on those which are not clickable now, there is no information. And this can be useful also in this stage when you decide which new project you would like to start, or how you would like to change adjust your material, change properties, improve properties of your material by adding other elements to it. And then you check and you see, okay, nobody yet investigated of gadolinium, neodymium, and gadolinium with helium. Yeah, that's clear why, but maybe I should try technetium. It's also nobody tried, but maybe so it gives you a hint whether it makes sense to try something or it doesn't make sense to try. First, you see, maybe you will be the first one who will investigate the combination of these elements with the others, or maybe you better should not try because this has too high temperature, melting temperature compared to your material, and it wouldn't make sense to try. So it's just helpful information. And just imagine you would like to ask Google, what is known, or no, what is unknown on the combination of aluminium with other elements? Which other elements nobody yet investigated in combination with aluminium? You never will get the answer from Google, but you will get an answer here. Now I selected the 3 elements which I wanted. I have different modes here. Now I'm in the mode as selected plus any other element, or as selected plus subsystems. That means I will take all binaries and unaries, or I can take only that what I selected, for example. And I can also add particular keywords if I want to specify my search to a particular topic. Let's say I'm interested only in thermodynamics, or I'm interested only in mechanical properties, and the rest has no value for me. So I can select here up to 3 keywords with different Boolean operators, and this will reduce my list, focus only on the topic which I'm interested. So in particular, if you're interested in the properties, this is very helpful. But at the moment, I will not do it because we want to have everything and on this particular system. Let me go just ahead with selected plus any other element. And here on the right side, you see some statistics. I go to the results. Search and see what information I can get there on the next screen. Sufficiently slow results of the search, and they are presented as a bibliographic list. You can conveniently work with this. You can limit it to MSI publications only. That means our full text publications, our own publications, and the rest which have no icons. These are publications from other sources like conference proceedings, journals. I told you we monitor about 250 journals permanently, and we extract information which is relevant for us for inorganic materials. You can limit the search by years. You can refine. So now we, in this search, took these 3 elements plus any other. That means we have here 3 component and more component, 4, 5, and whatever is available. You can limit it to, let's say, 4, just by number of elements, let's say, and you want to see only 4 component systems which are available here, then you will get the list. If we take 3, then according to our search, these are only these 3. You also can, this is an interesting feature, you can find related material systems which are in a way similar to the system which you are searching for, to this one. This would deliver with using the data ontology, find the similarities, and will deliver other list of other systems which are similar to the system under your question. But now I'm going to this ternary system. I just would like to show how the You can expand each reference and get detailed meta information, bibliography. You can, if your institution has a license to this particular journal, you get by a direct link, you can open the article. It's not provided by us. But we have abstracts, and this you can find here in each citation. If you can create a list, you go through this bibliography and say, okay, these 3 are interesting for me, the others are not. They appeared immediately here under this tab. And you can look into the list of your references which you created. You can continuously print it or save softwares like I try to close some. So this is the list which can be exported. And I go back to the so now we will open the document with the critical evaluation of gadolinium magnesium system, and we'll actually, so I expand it and the full text. Again, then we will lose, I'm afraid, even more time. I will close one. Ideally, for better understanding because of this audio problems also. So now this is the document with critical evaluation of this ternary system. And these are the typical chapters which help to describe the ternary system in this case. One of the chapters is, of course, binary system. In this case, there is a long and large discussion about the binary systems, which was important in this case. Let us look in the chapter solid phases. So before we go into the diagrams, so one of the most important chapters, of course, and in the process of critical evaluation to decide what solid phases are considered as stable and what are their temperature ranges of the existence and what is their crystal structure. So this results in the table of crystallographic data. I show it later, and the text. And here I just will show you the moments which actually show how critical is our evaluation. Yeah. In this case, there was in one publication, now I have to switch to my slides. And again, it is slow. Okay, I will show you. This is isothermal section, and the original publication has shown here at 450 degrees a solid solution between magnesium 5 gadolinium and magnesium 5 neodymium. There is a continuous solid solutions. And then we go back to this document, and we see that the existence of this solution is actually not, cannot be accepted by our authors. The neodymium magnesium 5 phase is not stable in the magnesium-neodymium binary systems. And therefore, this was rejected and not accepted by our authors. And another problem with this isothermal section, I go back to this isothermal section, this is this phase magnesium 7 gadolinium, which is also, according to the modern phase diagram of magnesium gadolinium binary system, doesn't exist, or it exists, but it is considered to be metastable. And this is the point which is also spotted by our experts. And at the end, when we go to the section about isothermal sections, to the chapter of isothermal sections, you will see here, this is the text. And so this is the description that this complete section was not accepted by our authors of critical evaluation because it was considered as not reliable. Because of this continuous solid solution between the phase, which doesn't exist anymore, and gadolinium magnesium 7 phase, which also is metastable. In some cases, our authors would be able to redraw and to find a compromise, maybe with some assumptions and suggestions, but in this case, it was not possible. Therefore, this temperature, 450 degrees, was kept. And if we look on other isothermal sections which are presented here, for example, just 50 degrees above the 500 section and the 400 section, 400 degrees section, then we see that it's really rather unlikely that in this 50 degrees between these 3 sections, there would be another continuous solid solution. And in particular, if the phase doesn't exist, it also wouldn't appear there. Therefore, this section in this case was actually not included in the report. And the table of crystallographic data reports only information about the stable phases which are existing. In case of binary systems, there will be also binary metastable phases listed. In case of ternary metastable phases, if they exist, but binary metastable phases are not listed. So this was one example. You can search, of course, in this document. You can check for whatever properties are reported. We don't make deliberate search for properties, and we are not pretending to be comprehensive with respect to materials properties. We find we take information about different materials properties in the literature which is related to materials constitution. So let me look on my slides, what I have here. Yeah, there is also an isoplat section, a vertical section at 3 mass% of neodymium. So this is the section as it is presented in this document, in our critical evaluation, and this is the original article on which this phase diagram is based. So first of all, our authors accepted only the range which was experimentally confirmed, and this is where we more or less see the experimental points. All others, this was considered as speculation, and therefore it was not reproduced here because that would be too much speculated. Also in detail, this text, if you look here, it describes in details at which temperatures, for example, the data at 500 degrees and above have been considered reliable due to the good agreement between different other publications also. And that was what was not accepted is very well described in the text with the details and showing some points. If you look here, for example, this phase border between magnesium and magnesium plus neodymium 541, magnesium 41, this border also has been modified by our authors slightly. Yeah, if you see this point is here coming exactly on 500 degrees, and here it is slightly, oops, sorry, slight. Now I'm back to, it is slightly above this temperature. What I wanted to show that we try to really find what is reliable, what is less reliable, and in some cases also what is less reliable can be presented if our experts consider this as feasible. But in some cases it is just skipped from the presentation. Now I briefly will show you our client software. This is actually the same. This is an alternative alternative interface to the database. The content is identical, but this client software has some more advanced feature for walking and reading phase diagrams. Can you see this window now? Can somebody confirm when I'm changing between different windows? Can you see now aluminium, magnesium, silicon?
Yes, ma'am, visible.
Thank you. So let's look what features are available here for the working with phase diagrams. So first is by simply moving a cursor on the phase diagram, I can read concentrations here, and they are displayed then in this window in atomic and in mass percent in green and red bars, and these values are changing. You can see when I'm moving my cursor here along this line, these values here are changing. Yeah, and this is very convenient. I can add grid and I can make it very often, so that just for rough estimation. An interesting feature is also magnifying glass, which I can put in the area which is more interesting for me, and still here, even in this window, I can read concentrations. If I want, for example, exact composition of this point, I can just put my cursor here, and again, I can read it exactly in this window. Except for that, I can convert the entire diagram. Now it is, as most of the diagrams are presented by default in atomic percent, I can convert them easily to mass percent by just clicking these two buttons, and then my entire diagram is in mass percent already. I go back. Another interesting feature is an overlay of diagrams. If we want to compare, for example, the character of phase equilibria, how it's changing with changing temperature, and then we take, now in this case I have 600 degrees as a thermal section. I can overlay 550 on this section and see what is changing in this 50 degrees. Now the 550 section appeared in the green lines, and we see that in this 50 degrees, so when the temperature increases up to 600 degrees, the liquid phase appeared, which was not present at 550. Therefore, the equilibria have changed. And this is, of course, a simple example. If you have a more complicated case, or you have liquidus and solidus projections, it's very helpful to overlay it to understand what is happening actually in the system. And another interesting feature, I can, for example, click in the diagram directly on a phase name, and with this click I will initiate a search for this particular phase through all tables in this document, and at the end it will highlight me. This is, for example, a table of invariant equilibria. So now I have in black highlight all invariant reactions in which this phase, which I clicked, magnesium to silicon, is taking part. This was one of the tables, invariant equilibria, and it will also allow me to quickly find it in the table of crystallographic data and also highlight it. So in some of the evaluation reports, there are also microstructures which one can view by clicking on them. Now I think I demonstrated you already all features. I will just quickly complete my presentation, MSI standards for critical evaluations of phase diagram data are adopted by EBDIC, Alloy Phase Diagram International Commission, where MSI is a full member, and we were choosing by leading publishers for producing scientific content for joint publications of many books by these publishers. And just a few words about the EBDIC. Maybe you know this. This is an organization which was created to promote quality standards for phase diagram evaluations and assist effective dissemination of data, and also promote the application of phase diagrams in industry and academia. EBDIC Commission, for example, gives every year awards for the best paper published on phase equilibria, and also best EBDIC Industrial Award for bringing phase diagram data to application. It has 18 members, this organization. MSI is one of them, and Indian Institute of Technology in Madras is another one. Now, just to summarize the unique features of MSI Eureka, the database, actually, which was my presentation is around it. It covers virtually all inorganic material systems which ever were studied, and it's over 75,000 systems. It has modern search interface allowing to search for targeted properties and other keywords. It has altogether more than 15,000 phase diagrams and other graphs, and it has largest bibliographic database in materials constitution with more than 493 citations, and it is continuously updating. And we are not limited by number of components. So we start with unaries, binaries, tenaries, and we go to more component material systems, whichever were studied in the world literature. We evaluate the entire material systems, not only phase diagrams, and our program has the largest number of evaluated material systems. It's 4,500 systems. And actually, this is the largest phase diagram program ever, which is going for over 35 years. The unique feature of MSI Eureka that it is made by scientists and for scientists. This I will skip. Now, at the end, just a few announcements which may be interesting for you. I mentioned already before that 5 years or 6 years ago, we started the new series of educational event, MSIT Winter School on Materials Chemistry. And the next winter school is planned for April 2022 in Germany. Most likely we will make it as a, due to pandemic, we will make it as a hybrid event, so we will accept on-site participations and online participations. More information I can provide you in the next nearest future, but you know, now the situation is changing everywhere very rapidly, so nobody knows how it happens. In the worst case, it will be again online. Last year, or this year in May, we made an online event, and it was very smoothly organized. Everything ran, all lectures were made perfectly. So that's, in any case, we have a solution for the case if we cannot meet. The approximate program is here. So we start with the basic principles of thermodynamics, of phase diagrams, and then we go into details of experimental determination of phase diagrams, detailed lecture on crystallography with hands-on and experimental methods in thermodynamics, and a DFT method, and at the end, 1.5-day computational materials thermodynamics CALFAT method. We take one real binary system. By the way, last year it was magnesium, probably magnesium copper. Probably next year it can be the same. And by the way, our main lecturer on this section on the CALFAT method is coming from India, from Madras Institute of Technology. During this experience of the winter schools, we realized that among our participants and in the material science society, there is interest to go in some topics in more details on a more advanced level, and therefore we are starting a series of MSIT advanced schools, and the first one is planned also for the next year. It will be in October, and the same location, Castle Ebenberg in Germany, and the program will focus on the diffusion couples, including simulation using DICTRA program. You know, we organized this event with the Thermocalc software company. So, so far I'm ready with my announcement. Yeah, registration will start in January. And again, a summary, and here I'm at the end of my presentation. Let's look if you have questions.
Participant, if you have any kind of questions, please do unmute yourself and go ahead. If your network coverage is very poor, then you can always write in the chat box.
Should I ask question?
Please go ahead, Mr. Pankaj.
Myself, Dr. Pankaj Kumar Singh from IIT BHU. Your lecture was nice. One thing I know about the MSI Eureka you are using, what is its full form?
Full form. This is a database, online-based database, and it is distributed as a with annual subscriptions. So the university usually, or an organization, a company, takes a license, campus license, which is available to all users within the organization. There are also licenses available for departments, and both interfaces are available. And the data which I included, these are data all related to materials constitution, to phase diagram. Different systems. It's altogether 75,000 systems, but on different level of information, different data categories. Did I answer your question, or?
No, that I understand. I want to ask that whether it is having some full form. MSI, what is this MSI Eureka?
Material Science International.
MSI, yeah, MSI is the name of our company, so Material Science International, and this is then also part of the name of the product of the database, MSI Eureka. Eureka is the Greek name of who was it? Archimedes, who found the volume of, so if you put a body in the water, then it drops out. Sorry, my English is not good. The same volume of water as the volume of the body. And when he found this idea, then he told Eureka. And it sounds slightly different in different languages, yeah. And Eureka, Heureka, Eureka. So that's the name of the database. So you just accept it as a commercial name of the database. But MSI is Material Science International.
Thank you.
Ma'am, you were discussing about lot of book series. Is those book series were open source materials, ma'am? Is anyone can access?
No, all books are commercial products, but they are available in many libraries, the academic libraries. So you can check in the previous years, the first at least 15 volumes of our book, Ternary Alloys, was the name of the publisher is Wiley VCH. So if you find it, these blue books, then these are our books. So you will find there the editor is Günther Effenberg and others, and you will distinguish them. If you have any questions, just write me. I can help you to find them. But these are all commercial products. And the other books which we made with other publishers, we didn't distribute, and we are not distributing them. So they are distributed by these publishers, whoever that was, ASM, American Society for Metals, or Springer. They distribute the books. We only produce the content, the scientific content. And we don't have open source products, open source publications, except for the few documents in MSI Eureka, which are available for, as a demonstration version. I can show you how to find it. You still can see my screen.
Yes,
If
ma'am.
you see here this search interface or whatever, you come on the first page, then you will start slowly open. So in any case, in this bottom, if you go, you will see the royalty-free license, and there you can see the list of documents which I included. It's not a couple of documents, so this is the very included for free. Yeah. On our webpage, you will find some other free content. Just go on the page msiport.com, and there you can find more. So this web page.
Thank you, ma'am. One more question, ma'am. You were talking about material science simulation software. What is the name of that simulation software, ma'am? Is there any student versions for that software?
We don't have our own software for performing calculations, but our authors, if they have license, they can use other softwares for different calculations. And the most common is either Thermocalc or Pandat softwares. These are the most, but there are also others like FactSage and others. And at the end, there is no difference. I can tell you what we are using in our MSIT Winter School when we make this CalFAT modeling. We had experience with using Thermocalc, but in the last years we realized that for the beginners who just start working in calculations, it is more easy to use Pandat, and therefore already the last 2 years and the next year we will use the Pandat software. It's from the USA, the database, the software. Yeah.
Thank you, ma'am. Thank you.
You're welcome.
Madam, I have posted in the chat box. See how many phases exist in the heterogeneous multiple component in equilibrium. Hello. How many phases it will exist? Exist in the heterogeneous multi-component.
It multi-component. So it depends in which area you are. If you have, let's say, single phase field, yeah, and this single phase field forms equilibria with another one, then you will have two phase field in between. If there is tire triangles, it means a three-phase equilibrium comes, then on the bottom of this single phase field, you will have tire triangles. So in fact, you will have two lines of the single phase field coming in one point, and from this point also, it's difficult to show with fingers, two tie lines will start. So the four lines can meet in one point. But this is again a question whether you are about a three-phase equilibrium. But in a ternary system, more than four lines cannot meet in one point. I see
Thank you.
somebody
Thank
is
you.
also asking about email. I will drop in the chat box
Yeah,
my
I only
email
checked the
address.
chat box. I sent it. Okay, madam. Thank you. Thank you.
If you
Okay.
have more questions, please don't hesitate to contact me by email. I will be happy to answer your questions. And I would like to thank again Rajat for inviting me to present activities of our scientific team. And
Thank you. Thank you,
thank you very much.
Svetlana. Yeah, thank you, Svetlana. It was an excellent talk on critical evaluation of data and all the relevant information that you provided. On behalf of JNNC and National Education Society, I'm extremely happy and I'm thankful to you for having participated for so long. Thank you very much. And I met Gunther Effenberg during 2009 in Russia. I had visited Mrs. MSIS. So there I was able to meet him and I spent a day, full day along with him. So I got to know him very well. Yeah. Thank you very much.
Yeah,
Thank you.
yeah,
Over
yeah.
to you,
I
Svetlana.
hope, Rajat, you can come and maybe your colleagues also to one of
Sure.
our next meeting. What I would like to mention is that the winter school or the advanced school, we probably will be able to make online, but our standard meeting where we make critical evaluation, unfortunately in the online mode is very, very difficult and not really efficient and encouraging. Therefore, that's a little bit critical, but I think we have to hope that maybe until April the situation will change.
Yeah.
And we would be happy to have also people from your department at our team.
Sure, sure, sure.
Thank you.
Thank you, Dr. Sujana, for a wonderful session on how exactly MSI can help our young budding researchers to know about materials and how exactly to conduct research and where about to look about. So any questions, again, as Dr. Suchilana has mentioned, you can directly contact her using her email. So coming to the end of this session, so we'll be meeting for the next session at 2 by Mr. Pramod Bingole. So until then, I wish you a very warm break. Okay. So thank you one and all, and thank you for a beautiful session, ma'am.
Thank you. Bye-bye.
Bye. So dear participants, we are going to meet at very sharp at 2 o'clock. The session begins at 2 o'clock. So please be away. Be sure that you log on to this session by 2 o'clock. And for each session, so you need to write your name and affiliation and your post in the chat box for attendance. Okay. So thank you all and have a very warm break.